Hi everybody, and welcome to going through the notes for the resistance packet that you just got. We're going to be talking about series, parallel, and combination resistors for this, and this is going to be based a lot on what you saw in the lab during our water circuit last period. So let's start with this. I would strongly encourage you to do the reading at some point. It doesn't need to be today, but before you get into the test, and definitely in general, I would say it's a really good idea to go through the reading. And if you're struggling with this stuff, the reading can help a ton. So let's start with the idea of resistance. So resistance is the opposition to the flow of charges or movement of charge. So we'll just add that right in here. Sorry, my handwriting's terrible on this, but that's okay. And the basic units of this is ohms. This is a kind of new, unique unit. You don't need to know what it's made up of or anything like that. It's pronounced ohm, and its symbol is a capital omega. Okay. Current, which we've talked about before, is the rate at which charges pass a given point. And this would be, in particular, we're going to be talking about positive charges. I know it's the electrons that move, but remember, it was Franklin who came up with all of these, what's positive, what's negative. So we're stuck with conventional current. And again, that is the rate, R-A-T-E, at which charges pass a given point. Its equation is the current, I, is equal to the number of charges passed a point over time. So its units would be coulombs per second, which is amperes. I'm going to just pronounce it amps whenever we're talking about that. That's short, that's pretty common. Voltage, we've done this one before. You should remember it. What is the definition of voltage? Voltage stands for the, you said it, electric potential difference. So electric potential difference. Again, it is a potential difference. Let me see if I can spell. It is a difference, but we have dropped our delta symbol. When we're talking in currents and circuits, you're going to be seeing it more as V for voltage rather than V for electric potential. And the units of electric potential, remember, are just our volts. And those units are capital V for short. Okay. Now, when resistors are placed, in what order is when they come one right after each other and allowing only one path for the charges to move? Do you guys remember? That's right, it's series. So in series, they come one right after each other. And the voltage across the resistors changes or varies with the resistance, while the current is everywhere the same. And we really did see that and that is so not what I wanted. It's the current that remains the same everywhere, and that is what we saw yesterday in the lab when we moved the flow meter around the paddle wheel, and we got basically the same flow rate at all the different locations. Now, alternatively, when resistors are placed in parallel, there are multiple paths on which the current can flow, the charges can move around. When they're in parallel, the current through each branch varies based on the resistance in that branch. The more resistance, the less current, because the harder it is to get through. But the key feature, the defining feature, what makes parallel, okay, of a parallel arrangement is that in each branch, the voltage across each branch is the same. The voltage stays the same while the current varies, and that's the opposite of what happens with series, where the current is everywhere the same and the voltage varies. Okay, so we've got that one down. All right, this is that key idea of what's going on for parallel, is that the voltage across each branch stays the same. Now, when you combine resistors either in series or in parallel, you can change the overall or total resistance of the circuit. That total resistance is known as the equivalent resistance. Equivalent resistance. And if you're like, I don't even know how to spell that and I can't read your writing, that's totally okay. Turn the page, and there it is. The equivalent resistance is the amount of resistance that a single resistor would need to have in order to replace all of the resistors in that combination to draw the same total current. You totally can read that. But the idea is, what we're going to be trying to do is replace all of the resistors, kind of combine them into one single giant resistor with a set equivalent resistance. Okay. Now, in order to do that, we're going to need to know how to add series in either, add resistors in either series or in parallel. And so you have the equation right underneath here. In series, again, when they're coming one right after each other, and let me get rid of the pointer here. Okay, so when they come all one right after each other, okay, and there's only one path, like the current comes in and it has to go through resistor 1, it has to go through resistor 2, it has to go through resistor 3, that's when they're in series, and it's super easy. You just add them together. Resistance 1 plus resistance 2 plus resistance 3. However, in parallel, when we're looking at parallel, the idea is the current comes in, it gets to this point, and then it's got to split up. It's got to make a decision. It can go up, it can go straight across, or it can go down. But the same charge can't go all three different ways. So this is how you're going to know. You're going to run your finger along, you hit oh gee, my finger has to make a choice. That's a parallel combination. At the end, they're going to come back together and then come out, and all the currents rejoined up, okay, again here. But for equivalent resistance, it basically makes it easier because there's a lot of different paths that the charges can go on. So here we add reciprocals. This is super important. 1 over the equivalent resistance for parallel is equal to 1 over Req plus 1 over resistor 1 plus 1 over resistance 2 plus 1 over resistance 3. Adding these together is going to be super important. Another way to think about this is that when you do this, you can say Req is equal to 1 over R1 plus 1 over R2, all of that to the -1 power. It's the same thing, okay? I kind of like this way myself, but that's mostly because that's how I enter it in my calculator. Okay, so adding these together, right, what you're going to do is, given this schematic below, figure this out. Okay, so we've got resistor 1, 2, and 3. They're all one right after each other, which makes this what kind? That's right, series. Okay. In series, we're going to basically be able to say R in series is just them added together. I'm going to skip trying to write out the generic equation right now because, as you can see, this is not the easiest thing I have ever done. So it's 10 plus 33 plus 70. And when you do this, you would get 33 plus 70 would be 103 plus 10 is equal to 113. And the units are ohms, okay? And that matches our answer right here, so we know we're good, all right? straightforward. When they are in parallel, okay, again, we've got charges coming in and they can go up or they can go straight. There's options. So this is right here, we get to this point. It's called a junction. There's different places it can go. And so this is going to be our parallel. All right. So in parallel, REQ would simply be equal to 1/330 plus 1/100. And if I were going to go through this, I'd have to find a common denominator and then multiply them out to get the common denominator, add them up, and then take the inverse of that. When I do that, I am going to get my 76. Wow, that's so bad. 76.7 ohms. Okay, as you can see, going through this, fairly straightforward. You have the rest of the period and what you don't finish in class I want you to do for homework to go through the rest of your examples, okay? But before you do, I do want to point out that you have one last thing to fill out at the bottom of this page. So after reading through the examples, something is definitely very, very clear. When the resistors were in series, like that was in that first example, the total resistance or the equivalent resistance, was it greater than, less than, or equal to each of the individual resistors? So how did the total resistance compare to that 10, the 33, and the 70 ohms? Okay, I want you to fill that in. In parallel, okay, the second example, when we had the 330 ohm resistor and the 100 ohm resistor, and we got that total resistance of 76.7 ohms. Was that total resistance greater than, less than, or equal to the individual resistors, those 330 and the 100? Answer that. Fill that in. You should be able to figure those two out by yourself / talk to your neighbor. You should be able to come up with these pretty straightforward, really good reminders of how you can check yourself. All right. Thanks. Good luck.